Hello, friends. This is 4-2 Matrix Edition. Here's a journal choice. You might like it, 4 to 6 sentences at least, and you can turn that in when you turn your quiz in on Friday. Okay. Objective and what's the point? We are going to introduce the operations of matrix addition, subtraction, and scalar multiplication. This is fun stuff. Pretty easy. Kids usually like this a lot and barely ever make mistakes on it. I don't want to jinx you, but I think that's what's going to happen. These are the fundamental operations in linear algebra, which I told you yesterday is a college course that a lot of people are required to take in a lot of math careers, and it is fun stuff. So, words to know. There's going to be a little bit of vocabulary here, but it's going to make everything today is going to make sense to you. It follows common sense. Matrix addition. We're going to take those matrices that we dealt with yesterday and we're going to add them. Here is the only rule that you really need to pay attention to. Not the only rule, but the most important. You can only add matrices if they are the same dimensions, okay? A 2 by 2 can go with a 2 by 2. A 2 by 3 can go with a 2 by 3. But a 2 by 3 cannot go with a 3 by 2. You have to have the same dimensions. And the reason being is because each element you're going to add with the corresponding element in the other matrix, okay? When I do an example here, you're going to be like, well, dumb, Miss Bruno. But I just want to make sure that you don't try to add things if they're different sizes. Okay, so here's the process. You're just going to add like elements and you're going to put them in the right spot. It is commutative. You can take matrix A and add it to B, or you could take B and add it to A. I'm going to go ahead and throw an example up here. Let's call this one A, and let's call this guy B. I'm going to go with 2 by 2 matrices here. 1, 2, 3, 4, real creative. And how about negative 1, 4, negative 3, 7. Okay, I can add them. A plus B. What is A plus B going to equal? Well, it's going to be the same size as what you start with. So it's also going to be a 2 by 2. You're just going to take the 1 and add the negative 1. That's 0. And you put it in the same spot. So first element here with this element, put in that spot. 2 plus 4, 6. 3 plus negative 3, 0. 4 plus 7, 11. This is our solution of A plus B. Okay? It doesn't matter if I take A plus B or B plus A. I can switch it around and I'm still going to get the same result. So that's what it means by being commutative. And is also associative. If I threw in a third matrix, it doesn't matter the order in which I add them. As long as I add them all together, we will get the same answer. Okay? Let's talk scalar multiplication for a minute. What does 3A mean? Okay, 3A means A plus A plus A. So if I was looking at 3A, I could write this out 3 times. 1, 2, 3, 4 plus 1, 2, 3, 4. I'm going to throw the other one over here because I'm short on space. Okay, and I have 1 plus 1 plus 1. That is 3. 2 plus 2 plus 2, that's 6. That's funny. That's an email. Could you hear that? I'm curious. 3 plus 3 plus 3, that's 9. And 4 plus 4 plus 4 is 16. That's so perfect for the matrix lesson because that sounded like superpower-ish. I don't know if the matrix is superpowers, but here's the answer. 3, 6, 9, 16. Now, nobody wants to write those out 3 times. That is not fun for anyone, and I really love math. So what you can do instead is you could just take a 3, a constant 3, and you can multiply it by the 1, 2, 3, 4, just like you would do with regular multiplication, and you kind of super distribute this guy in here, and you're going to get that same thing we just did after adding 3, 6, 9, 16. It's so much easier and so much more fun. Okay. I like it a lot. Okay, I hope you do too. So that is scalar multiplication in a nutshell. Let's look at matrix subtraction. Matrix subtraction is a little trickier, but it's not hard. Let's throw up some more matrices again. 1, 2, 7, 11. And that's going to be A, and this time let's make B 4, 4, negative 3, 2. Okay, this time I'm going to subtract A minus B. Now, when you do this, you have a couple of options. You can just subtract each element. 1 minus 4. 1 minus 4 is negative 3. 1 minus 4, negative 3 again. 7 minus negative 3 becomes plus a positive, so that's 10. 7 minus 2 is 5. You can do that. But I'm going to ask you to consider doing it this way. Go ahead and think of this as a negative 1 outside, and I want you to change all the signs instead. The reason I'm going to ask you to do that is because I've graded a lot of matrix addition problems. Kids tend to maybe subtract the first term and then just go automatic pilot to addition. You get used to adding matrices because it comes up a lot, so then you go and you make a silly mistake. So I'm going to instead just change all the signs, negative 4, 3, and negative 2. Then I can add them. You'll get the same answer. 1 minus 4, we said negative 3. Oh, why didn't you tell me I made a mistake here? Because nobody listens. 2 minus 4, that should have been negative 2. Negative 2, 7 and 3 is 10. 11 and negative 2 is 9. And I did that wrong too. Where did this 5 even come from? I don't even know. Well, now you're probably all thoroughly confused. And nobody even told me I made a mistake before. 1 minus 4, negative 3. 2 minus 4, negative 2. 7 minus a negative 3 is 10. 11 minus 2 is 9. 5. Okay, I'm embarrassed. But anyway, I hope that didn't confuse you further. If it did, I'll clear it up tomorrow. My bad. Okay, so that's matrix subtraction. I'm going to encourage you again to change all the signs in your second matrix, the one you're subtracting, and then think of it as addition. Or you could subtract each element. I just don't recommend it. Okay, so let's look at an example. This is so much fun. Okay, first thing, can I even add these? Are they the same size? This is a 2 by 2. This is a 2 by 2. We're good to add. So we're going to go ahead and add the elements in the right spots. Negative 2 and 1. Negative 1. 5. Negative 3. 2. 0 and 8. 8. Negative 7. Negative 2. Negative 9. Superstar. Good job. Okay, this one is a little trickier because you got a couple of things going on. You have a scalar multiplication, and then we also have, which will become a subtraction, addition sign after we distribute. So let's go ahead and write it down below after we go ahead and multiply. So everything's going to be multiplied by this negative 3. I have 0, negative 3, negative 3 halves, and 6. Hope I didn't mess up. 0, negative 3, negative 3 halves, and 6. Okay? Now I'm going to go and multiply the entire second matrix by negative 4. That way I can have an addition sign when I'm done. That gives me negative 1, 0, negative 3, and 4. Double checking. Negative 1, 0, negative 3, 4. Finish the problem by adding negative 1, negative 3. And let's change this to negative 6 halves. So that becomes negative 9 halves and 10. This is my final answer, and that was a lot of fun. Okay, so these problems aren't difficult. Be careful. You might make a silly mistake like I did on the previous slide. And the only thing that could really cause you a little bit of a trip up, I think, would be the scalar multiplication, especially if there's a negative there. Okay, here's a real world example problem. Like I said, matrices are a lot like spreadsheets. They store data for us. So this is an example of something maybe a guidance department might use, or any school administration when you're tracking your enrollment based on grades. Okay, so this could be helpful for a variety of reasons, and this is how they sort it in 3 matrices. N1 is the first year, and N3 is the last year. They have, if you'll see here, the rows are separating the gender, boys and girls, and then the columns are separating the grades. These labels here, this grades, you could put gender beside here if you want. Sometimes that's helpful. Like obviously you didn't need it as much for boys and girls because you knew what they're doing here. But the 9, 10, 11, 12 might not make a lot of sense to everybody, so that's why they went ahead and put the label there. This N1, N2, N3, it's not necessary to give your matrix a final name, but it is helpful in problems like this when you're dealing with more than one. That way you can just refer to one of the matrix. When I say, let's look at matrix N2, then people know which one I'm talking about. Okay, so they want us to find a matrix T that shows the total enrollment. So this is like the total matrix in each grade by gender over the 3-year span. So this is asking us to consider what is N1 plus N2 plus N3. Okay, these are all, we can add these because they're all the same size. These are 2 by 4 matrices, row by column, if you remember RC COLA. So 2 by 4, and they're all the same size. So my final answer will also be a 2 by 4 matrix. I hope I have enough space. I'm going to pull out my calculator here. Okay, because when I add these, I'm going to add 289, the 240, the 154. Okay, I got 683. There is going to be a chance I make a typo and no one will be here to correct me. 299, this one's going to go with the 240 and the 143. I have 682, 282, 228, 149, 659, 288, 234, 143. Okay, so if you see, I've got the squares going here, the squiggly lines. I think you can see where they match up now. I don't think I need to separate them anymore for you. 276 plus 216 plus 143, 635, 276 plus 228 plus 138, 642, 270 plus 264 plus, oh, that's not right. 270 plus 204 plus 138. I feel like I'm making mistakes now. I'm all self-conscious. And 264 plus 222 plus 132, 618. Okay, what is this representing? Again, these are your grades. This is the total over the 3 years span. They're telling us to call this matrix T now. And we're talking about boys on top and girls on bottom. So what was the change in enrollment for boys and girls in each grade from the first year, which this was the first year, I think, to the last year? Okay. You have a couple of options here depending on how you want to represent. I would say that I would take N3 minus N1 personally. You obviously have the option of taking N1 minus N3. If you're talking about growth, then it would be different value assigns. But what I'm going to do is I'm going to take N3 minus N1. And you can see that the enrollment's going to go down. You should be able to notice that before you start. Okay. I am going to go ahead and change all the signs here and add them. So 9 boys, let's look at what we got here. 154 minus 289. Enrollment went down 135 from the first year to the last year. For girls, we have 143 minus 299. Again, it went down 156. Okay, if you want to just express it in a positive change, you could have gone the opposite direction there. Okay, I'm not going to finish this problem out because I think you understand what we're doing here. I think everything would have gone down, yes, because we're all in the 100s in that third year. Okay, this is just an example of a real world situation where you can use matrices, addition and subtraction, to express data. Okay, this example, these are my favorite. we are going to solve f equals kg, and we're going to try to figure out what k is. So we're just going to plug things in just as it looks. F is 1/3, 1/6, 1/9, 1/12. K is what we're looking for. Equals, forgot the equal sign there. And G is 1, 1/2, 1/3, and 1/4. Okay, I can distribute K all through this if I want. Basically what will happen is I will have 1/3, 1/6, 1/9, 1/12. I kind of out of space here. And now I have K, K over 2, K over 3, and K over 4. You only need one piece of the matrices to figure this out. And if you see, the best piece to use is this K equals 1/3. This piece has to equal this piece because that equal sign is saying it does. So I've already figured out that K equals 1/3. You did not have to use that piece. You could have said 1/6 equals K over 2, but then you would just have to multiply both sides by 2, and again, you're going to get K equals 1/3. It doesn't matter which element matchup that you use, but try to find one that's the easiest, such as the K is already by itself is 1/3. Okay, let's try this one. Solve G equals LF. G is 1, 1/2, 1/3, 1/4. It equals L, which is what we're looking for. F, 1/3, 1/6, 1/9, 1/12. Okay. This one's not as easy, but it's not hard. L over 3, L over 6, L over 9, and L over 12. Okay, find a piece you like. Again, I'm going to pick with a 1 equals L over 3. Get L by itself, multiply both sides by 3, L equals 3. And you can see this makes sense. 3 over 6 equals 1/2. 3 over 9 equals 1/3. Okay, these equations with matrices are usually really fun to solve, and they're not that hard. I think you'll like them. Oh, I didn't want that to happen. Let's do that instead. Okay, how about this one? Solve for A, B, C, and D. This is another equation I was talking about. You got to match things up. A plus 17 equals 21. That is your equation. This is very easy for us to solve. Subtract 17, A equals 4. Okay, how about this one? 18 plus B equals 81. So I have 18 plus B equals 81. Minus 18, minus 18, B equals 63. Next one, 54 plus C equals 25. This one's going to be a negative value. (25 minus 54 is negative 29. And the last one is 35 plus D equals 30. D is negative 5. Okay, again, not too hard. I think you'll like it. I think that's all I have for you today. Okay, enjoy. See ya.